So here's your recap of the marker lab. Hopefully you remember what you did. You rolled off a marker, so you gave it initial velocity, which was strictly horizontal, and measured the height. So this was your, let's say I used 92 centimeter height. Remember, you need to make that meters. If you don't, then your time is going to be 10 times longer than it actually was. 0.92 meters. And let's say I whacked my marker so that it landed, let's go 75 centimeters away. 0.75 was the displacement horizontal. We know, we talked about what projectile motion is. It's free falling while moving horizontally. We assume that there is no air resistance, therefore there is no acceleration horizontally, and Vx is constant. Vy is changing due to gravity. Acceleration of gravity is negative 9.8 meters per second squared, and that force of gravity accelerates us at that rate. So general formula for change in y for vertical, remember we are talking about accelerated motion, is V initial, and if you want to, you can say y times time plus 1/2, and generally it's acceleration, but we're going to use g because we're talking about vertical acceleration, and projectile motion implies that acceleration is equal to g. And then change in t squared. Modified for a horizontally launched projectile. If it's horizontally launched, then this is 0. So that negates the entire thing. And we have a shorter version of the formula, which is 1/2 gt squared. From here, you have two options to find t. It's going to be root for both, but you can do two changes in y over g, or you can do just change in y over 4.9, which is half of g. So those are your options. How did I find that? I multiplied everything by 2. That's your change in 2 in change in y over g. That was t squared, and then I rooted both sides. That's how I found it. Or I figured out that this is 4.9, so then change in y equals 4.9 t squared, so t is root of y over 4.9. So that is something that you can memorize if you want, or just practice deriving. Right, so calculations. 92 centimeters converted to meter over 4.9. 0.43 seconds. And I'm keeping 2 sig figs because 9.8 was 2 sig figs, and my vertical displacement was also 2 sig. We need to find the initial velocity with which the marker was knocked off the desk. Because there's no acceleration, the formula for Vx is going to be change in x over change in t. So change in x for all of you, because you had your own turns, even though your time was the same, your distance, so for me, I decided it was 75 centimeters, so 0.75 over 0.43, so 1.7 meters per second. That is the velocity with which the marker rolled off for my imaginary example here. Now in part 2, we just wrote the general information about projectile motion, and specifically horizontally launched projectiles. For your markers, they did not land at the same distance, and then whoever, so I don't know, yours. Whose projectile stayed in the air longer? Nobody's. And why is that? Because when we looked at the general formula, so the general formula, remember, is this. V initial, and for all of you, you shared the same vertical displacement because you used the same desk. You all knocked it off horizontally, so initial velocity was 0. We assume no air resistance, so all your markers had g as acceleration. There's no way for time to be any different for any one of you. So all markers spent, providing they were knocked off of the same table. Those markers in one group all had the same time. So y, that was same change in y, g, and v initial y equals 0. So if everything is the same, change in t was the same. Now challenge. Is a projectile accelerating horizontally? Remember, this is free fall and moving horizontally at the same time. There's no air resistance. No. And then look at that magic, non-accelerated, because no air resistance. No air resistance. Was it accelerating vertically? Duh. G equals 9.8 meters per second squared was the acceleration. What was the horizontal velocity of the projectile right before it struck the floor? If I am saying that there is no acceleration, that means that Vx is constant. Well, whatever I whacked it with off the table, that is what it has. 1.7 for me. Whatever you had is going to be your answer. Whatever you calculated for your horizontal velocity, that's the answer. We're going to derive the final vertical velocity. So remember, V initial y was 0 because we rolled it off horizontally. And then for me, my change in y is 0.92 For some of you, it was the same. What else? I know we figured out that the time was 0.43 seconds. The easiest one, G equals V final minus V initial over time, from where V final is V initial plus GT. Well, V initial is 0, so 0 plus 9.8 times 0.43, that's about 4.2 meters per second downward. You're welcome to make it negative if you so desire. The next equation, we have this change in x, but I'm going to replace it with change in y because I remember it's going to be vertical. So V initial vertical plus V final vertical divided by 2 times time. For me, it was 0.92 times 2, multiplied that, divided by time, which was 0.43, equals 0 plus V final. How much do you want to bet it's going to be 4.2? Ah, 4.3. Okay, 4.3 meters per second. That is because I rounded the time. Anyway, then I also have the equation V final squared equals V initial squared plus 2G change in y, from where V final is going to be a root of 19.6 times 0.92. That is 4.2 again. I'm going to use that because I got it twice. Find the final velocity. So I know that final velocity will have two components. We already talked about how Vx doesn't change, and for me it wasn't particularly big. And here is my final velocity that I'm after. That is what we need to find. This is going to be a hypotenuse, so V final is going to be a root of Vx squared plus V final y squared. So for me, it's 1.7 squared plus 4.2 squared. For some of you, because the marker didn't travel that far, your final with 2 sig figs ended up being the same as your Vy. Well, so be it. Keep it that way. For me, it's 4.5. So 4.5 meters per second. And now I need to figure out the direction. The direction looks like we've been saying that it's south of east, but that's geographically. And this is just into the ground. So you can say below horizontal. Below the horizontal, and this will be 4.2 over 1.7 inverse tangent. Got 68 degrees. So 68 degrees below horizontal. Right here is my 68 degrees. And this is 4.5 meters per second. There you go. This is your recap of the work in the lab.